capacitance. We talked about how the capacitance is the charge per volt that a particular pair of conductive objects can accept. And for parallel plate capacitors, we have specifically that turns out to be epsilon times the area of the plates divided by the separation between the plates. And in general, for capacitors, we find that it's always going to have the form of epsilon times some geometric stuff. Okay, so what's magic about epsilon? How come a dielectric allows us to hold the same amount of charge with less voltage between charges? I thought charges are sources of electric fields, right? A charge sets up an electric field. It points out in every direction. If you have a lot of different charges, it can have an electric field distribution. But since when do charges have a variable amount of electric field? Dielectrics are when. And here's how this happens. Let's say we have a capacitor. And it's set up so that we have a fixed amount of charge on these plates. We have a plus Q on the top plate and a minus Q on the bottom plate. We have an electric field that arises in between these plates because of this charge distribution. Everything is fine. So we end up with a particular voltage because of that. And that voltage is going to be, as you know, the negative of the line integral from the minus plate to the plus plate. That's all well and good. What happens when we add a dielectric to this situation? So I'm just going to add a slab of dielectric material in here. Let's talk about what happens to the molecules in this material. The molecules are composed of a core of stuff that is positively charged, and they're surrounded by an electron cloud that is negatively charged. In general, this tends to be distributed so that it doesn't really have any particular polarity, or it might have some polarity, but they're not all lined up with each other. They could have, like in the case of water molecules, you might have an oxygen and two hydrogens, but all of the hydrogens won't be pointing in the same direction. That all changes when you apply an electric field. If I apply an electric field to this molecule, what happens is that electron cloud that's around the molecule gets sort of stretched out. So it sort of looks like this now. And now there's an area up here at the top with a net negative charge. And an area down here at the bottom with a net positive charge. And this separation of charges sets up an internal electric field that we're going to call EB because it's related to the bound charges that can't move around. That is in the opposite direction from the external electric field. And let me talk about what happens with with polar molecules or ionizable things. So if you have polar molecules like you do with water, what happens is all of these polar molecules already have one side that tends to be positively charged and one side that tends to be negatively charged. And your molecules will just all sort of line up more instead of being oriented in random ways. They'll just sort of all have their hydrogens on one side and their oxygens on the other side. I'm drawing these wildly different sizes. Sorry about that. But that is what happens when you have an electric field applied. In this case, the electric field would have to be that way to get the positive charges to all be on that side. Okay, so what does this mean in the context of our capacitor? What we end up with are a bunch of uncanceled negative charges on this top edge of the dielectric, and a bunch of uncanceled positive charges on this bottom edge of the dielectric, despite the bulk dielectric in general being electrically neutral. In this region in the middle, the negative charges of one molecule are close to the positive charges of the next molecule, so it's pretty neutral there too. It's only at the edges that you really see anything going on. So this sets up something that we call the polarization vector. I'm going to draw it in blue down here so you'll be able to see it. The polarization vector points in the same direction as the external electric field, like that. We call it P. And it has units of electric flux, and just like the electric flux density. So coulombs per meter squared. And it accounts for these extra bound charges that are affecting our total charge count here, where the electric flux density is now going to include the polarization vector and the electric field due to the free charges. The polarization vector is in the same direction as the free charge electric field. And it's proportional, and it's related by epsilon naught times something called chi epsilon times that field. This chi is called the electric susceptibility. So what this works out to is that you end up with the free charge electric field times epsilon naught times 1 plus that susceptibility. And we name this number the relative dielectric constant, or the relative permittivity. We can also call it just the dielectric constant. And because of the relative that is right in the name, we call this epsilon r. So that means that for the same electric flux density, which we get from the same charges, in the presence of a dielectric, we get less electric field, which means less voltage. Or if you want to think about this in a positive way, for the same voltage, a capacitor with a higher dielectric constant can hold more charge. It has higher capacitance, higher capacity for charge.